Alright, in this video we talk about algebraic properties of matrices. Since we started talking about matrix multiplication, we should also consider the properties such as associativity, commutativity, and so on. We know that we can add matrices, but now we need to talk about multiplying. It turns out that matrix multiplication is associative. This is the usual associative expression. You can replace x, y, and z with matrices. And you can prove this using the summation notation with components that we've been using in previous sections. If I take matrix M multiplied by matrix N, I have this summation expression. Notice that the column index on the first index in matrix is the same as the row index on the second. If I multiply n times r, I get this matrix here. So if I plug mn in here as the first part of my multiplication of mn times r, I'm just doing a substitution. Right? This here is going to be the ik component of the product mn, and I multiply that by rkl, so that's going to give me the il component of the product. So here I can basically combine the sums. This is repeated sum. I can just do the sums together and get this result. I can write this as a double sum over terms that are product of three entries. And that is just the same, and you can work out that that's just the same as if you multiplied nr first and then multiplied on the left by m. Doesn't matter because the double sums still combine. Okay. However, matrices do not commute in general. Sometimes they do, but most of the time they don't. Here's a very simple example you can work out. But this is interesting in terms of three-dimensional rotations. We saw previously that a rotation in two dimensions has this matrix here. Now, rotation in two dimensions is like rotation in the xy plane. You can see this rotation, which is a counterclockwise rotation by theta, in three dimensions looks like this. This one here with the zeros means that the z-axis doesn't move, but the x and y coordinates rotate counterclockwise by theta in the xy plane. Similarly, here we have a counterclockwise rotation about the x-axis. And here we have the y and z. So this would be a rotation in the yz plane. Okay. So these really are three-dimensional rotations. Now, if you rotate by this one first and then this one, is that the same thing as rotating by this one first and then this one? And the answer is no. Okay. Here's an example where m corresponds to 90-degree counterclockwise rotation about the z-axis, where theta is pi over 2, and n corresponds to 90-degree clockwise rotation about the x-axis, where theta equals minus pi over 2. All right, now if you worked out the algebra, it's a little bit complicated, but you can just take a block and see how this works. Okay, so first of all, m, 90-degree counterclockwise rotation about the z-axis. So your z-axis is straight down here. Counterclockwise means you turn rotating in this direction, like this. That's why this yellow is opposite from the green. You can't see it in this picture, but the yellow is the face over here on this side, as I said, opposite to the green. Then if I rotate n clockwise about the x-axis, well, the x-axis is the one coming out of this yellow. Originally it was coming out in this direction out of the red. Now it's coming out of the yellow. So it's going to tip up. This pink, which is the other side of the red, will tip up to the top, and I'll get this block here. All right, so this is a 90-degree counterclockwise z rotation followed by a 90-degree clockwise x rotation. Let's do it the other way. Now let's do a 90 degrees clockwise x first, followed by 90-degree counterclockwise z. 90 degrees clockwise x is going to tip this yellow face up to the top, so it looks like it's up there. And then I have rotation I have counterclockwise about the z, so my z-axis is here. Counterclockwise means that the other side of this blue face, which is this light blue face, comes here. So obviously these two orientations are not the same. You don't believe it, work it out yourself, go get a book and do it. But they do not commute. Now I should mention that M followed by N corresponds to the matrix N on the left multiplying M. And the reason is that matrix multiplication is like function composition. You do in reverse order. If I want to do M first, I multiply N and then multiply it on the left by N. So if I want to do N followed by M, that would be Mn. All right? So that gives us this example. Good example, something to think about.